Hello and good day. This is Chris Casano from Cockroach Labs. I'm a sales engineer and here today to talk to you about how to scale your writes onto CockroachDB using Apache NiFi. These two technologies work really well together, and that's why we call this a peanut butter and jelly story. So why CockroachDB and NiFi? Well, two things. First, CockroachDB is a geo-distributed database that can serve your applications and users for mission-critical types of activities. And Apache NiFi can deliver mission-critical data to wherever you want to store or utilize information. So if you wanted to utilize information in CockroachDB, Apache NiFi is a great way to get data into CockroachDB. So what this allows us to do is to do data ingestion rather easily. It can also help us do database migrations into CockroachDB. And it also enables being able to do hub and spoke architectures with Cockroach. And I'll get into some more of these details in the presentation. But first, a picture is worth 1,000 words. And think about how you would actually scale out a warehouse for a retail business that you might have. So here we have Cockroach Bill and NiFi Nancy, and they are stocking their warehouse in their single store. But as they scale up, let's just say they get to Amazon type scale where they have tons of warehouses and lots of stores and lots of inventory and items, being able to add items onto the shelf, one item at a time is a pretty slow process and might not scale with having thousands of stores. And this is very similar to how data works in a database. If you insert one record at a time, it can be a pretty slow process if you don't optimize the pipeline. So think about this picture and what you can do, or what Bill and Nancy can do to scale out their retail stores. Okay, and we'll come back to this in a little bit. All right, so what is CockroachDB? It's there's a lot of databases in the world, but this is something that's rather unique. So CockroachDB is a resilient, geo-distributed, consistent database. So what does that all mean? If you look at the map on the right-hand side, we have a picture of the world and all these different cockroaches all over the world. This actually represents one database instance that's actually spread all across the world. So no matter where you enter the database, whether you're from in LA or in Melbourne, Australia, the database all looks the same to you. And the fact that it can be geo-distributed allows us to connect all different parts of the world to have super low latent reads and writes as well. The idea behind all this is to make data easy. One thing that's always been hard in the relational database world is replicating data into different locations of the world. And the idea behind Cockroach is to make data easy to do this. A lot of the intelligence that went into this product comes from our founders who are ex-Googlers, and they worked on many of the distributed database projects over at Google. All right, so why Cockroach? Why another database? It really comes down to these four major points. First is resilience. If you think about a cockroach is a very resilient animal. It's very good at replicating itself and surviving, all sorts of different types of scenarios. CockroachDB does the same thing. It's great at replicating data across the cluster. If a node or a data failure happens, it's great at being able to recover from that. And it patiently will replicate itself and make sure that it can fulfill transactions and reads for the end users and applications. The next piece is consistency. So if someone is reading the database from Beijing and another person is reading the database from Los Angeles, when they look at the account information, they're going to get the same consistent answer in both ends of the world. And this is because we use serializable isolation in our transaction layer, so making sure that transactions are always consistent. The database is not eventually consistent, it's always consistent. Next piece is SQL. The world loves SQL, and the CockroachDB uses the Postgres wire protocol so that you can query the database readily. And the last major piece is geo-partitioning. This is being able to not only have the database work all over the world, but also being able to partition data to only exist in certain parts of the world. So for example, in the EU or in Europe, there is a lot of data locality or data sovereignty rules where data has to reside in the country that it originates in. And in CockroachDB, we can partition tables to keep data that might be country specific in the country that it resides in, thereby following the regulations, but also allowing you to query that data across different parts of the world. Okay, so let's go back to our picture and talk about how we actually do writes into the database. Well, since we are SQL enabled, you can write a regular, insert SQL statement like you see over here in the top left. And this equates to just how, Bill and Nancy would actually put a blanket up on the shelf, right? You create an insert record, it has a couple of values, and then that information goes into a table. There are several ways that you can do writes in the database. There's essentially two ways that you can do writes into the database. The first is through transactions, and the second one is through bulk loading. We're not going to cover bulk loading today. We can certainly do that another time. But on the transaction side, there's some key principles to be aware of. So we follow ACID transactions. We have transaction records that will be passed to the different nodes to support atomicity, and I'll explain a little bit more about that later. Like I mentioned, the database is always consistent because we use serializable isolation. And we achieve write consensus by using graph groups to ensure the durability of data between the different nodes on the database. And I'm going to explain this more in detail in the upcoming slides. But the last thing is that we do this all in a single round trip, which makes the writes for the geo-distributed database super fast. All right, so how does this all work? Well, first, every node or every server that's part of the database is a gateway for the entire database. So if we have a 5-node cluster like you see here on the right-hand side, that represents a single database instance. No matter which node or server you go to, the database will look exactly the same no matter what node you're on. There's no concept of master-child within this setup. Every node is consistently the same or a gateway to the entire database. We store data, data from tables and indexes in 64 megabyte ranges. They're not always 64 megabytes, but they're generally towards that upper threshold. So the data in these ranges are actually sorted by primary key, and that helps us helps enable lookups and range scans to be really fast as you're going to look up data within the database. Additionally, each of these ranges are replicated 3 times by default, and you can increase that replication if need be. And lastly, each of these ranges has an elected RAF leader. And that leader is responsible for coordinating any writes that come into the database. So as a write comes in, the RAF leader will decide how to begin and coordinate that transaction. And I'm going to explain how that transaction process works. All right, so let's talk about the transactions, which is part 3. So if we have a cluster like we have over here on the right-hand side, you can see we have a couple of different ranges where, and again, the ranges make up the data that are stored in tables and indexes and so forth. So we have several different ranges. We have a green, red, yellow, and blue range, and each of them have their own different RAF leaders, which may reside on different nodes. What will happen is if a request comes in to write data into a table, that request can come in on any node. So in this case, we're showing that on node 3, there's a request coming in to write. What will happen is that the node 3 will actually route that request to the particular RAF leader for where that data needs to be inserted into. So right now that request is being sent over to node 1, and where the RAF leader resides for the green range. That RAF leader is going to create a write intent and a transaction record that is then going to ship out to its replicas. Again, if you're not familiar with the RAF protocol, it's a way of driving consensus between odd parties of 3 or 5. So the idea here is that if we have a consensus write, which means 2 out of the 3 ranges, we can confidently commit that transaction to the database to say that yes, that record has been transacted or committed into the database. So what happens from there, after we send out those write intents to the other ranges, an acknowledgement needs to come back to the RAF leader that initiated the write to let us know that it acknowledged that the write can happen. And at that point, the RAF leader will decide that the write is committed, and will respond back to the originating node that the transaction was committed, and then ultimately tell the requester that the transaction has been committed in the database. So you can see here we have a single round trip used to do the entire write. It is a two-phase commit, but it is implemented as a single round trip. All right, so that's how writes work in the database. And again, go back to thinking about how you can scale this up, right? You have a distributed database, you have ranges across all these different nodes. Start thinking about how writes here would make a little bit more sense. All right, so if we take what we learned on having a distributed database with ranges all across those nodes, let's discuss how we can scale these things, right? Obviously we can add more Bill and Nancy's to the picture here to help out with adding more items into the shelves, right? That would help, add more records or blankets faster into the shelves. There's other things that we can do as far as even putting the blankets in boxes and then putting them on shelves, right? That would make things maybe go a little bit faster. We can add more shelves. We can add more warehouses. We can even compress the blankets, right? To make storage a little bit smaller so that we can fit more items in a box. So these are all things that warehouses would do to optimize their inventory, and it's the same type of thing that you can do with databases. So let me just get into some more details based on those topics we discussed. So if we add more Bill and Nancy's to help with stocking the warehouse, this is equivalent to as just adding more threads to the process of doing writes. And I'll explain how this works within Apache NiFi in just a moment. Additionally, we can have batches, or we can put those blankets in a box, and that would signify a batch, right? So you can think about a batch insert that you would do in a database, very equivalent to just putting things in a box and then putting it on a shelf. Like I mentioned, we can do compression. We can vacuum seal those blanket bags and make things smaller in the box so we can fit more items in the box. So that's another strategy that we can use here for scaling up the writes. We can also localize the writes, right? If Bill and Nancy have multiple warehouses right now, if they have inventory coming from a supplier that's in Jersey, and they have a warehouse in Pennsylvania, it would make sense to take the items coming from Jersey, put them in the Pennsylvania warehouse, as opposed to shipping them to a warehouse that might be located in Seattle. All right, so localizing those writes is always going to be faster for getting things on the shelf. The last two items are very similar, right? So one is being able to do random key distribution. So what does this mean? This essentially means using more shelves, right? So go back to that picture we mentioned before. If you look at a range as being a shelf, if we're putting all our blankets into one shelf, it's like writing all data into one range, which can be contentious. If we have a distributed database, we should be able to write to multiple ranges, right, to scale up the ingestion. And that's what the last item is. When we have more shelves, being able to spread that load across all those shelves, or being able to spread that load across a whole bunch of ranges, load balancing will help us get there, right? So those are the main items that can be used to scale up your writes in the database. All right, in just a moment, I'm going to come back and we're going to talk about how we can do this all in Apache NiFi, and we will see you in just a minute.